So, hi everyone, welcome to today's session on linear algebra to geometry. Let's wait for a few more minutes so that others can join. Hello. Am I audible? Everyone, please confirm. So, in the last session, we saw some theory notes on the few topics that were covered in the previous weeks. So, I hope my screen is visible, right?
Yes, sir.
Okay, fine. So, so let's finish up some problems and then we can proceed. So, these are few problems from week 8, right? Right. So, consider the vector space V equals to R2 and we define a vector's addition. So basically, in vector spaces, two operations are defined. One is addition, and the other one is a scalar product, right? Vector scalar product. And based on that, we have some interesting properties that we use. So for this problem, we have changed the properties to. So we have changed the addition property to something and the multiplication property to something, right? And then the question is, what is the zero vector in the vector space? So what is the definition of a zero vector? Basically, let's say you have a vector u1, u2. Then if you add it with the negative of u1 and u2, you should get the zero vector, right? So this is the idea of zero vector. So let's simply do this. Also, if you take a scalar product with zero, so this should be this and zero into this new vector product. The scalar vector product should be resulting in zero. Let's try to solve this and see what we will get the value of k, right? What is the value of zero, right? So let's see. So yeah, let's write this. So u1, u2, new operator and minus u1 minus u2 is essentially is equals to u1 minus u1 plus 1 and minus, sorry, u2 minus u2 minus 2, and this quantity should be equals to 0, right? 1 minus 2 is the answer, right? Then what is the meaning of 0 and 2? u1, u2. This will be 0 u1 plus 0 minus 1, 0 u2 minus 0 plus 2. u1 plus e1 plus 1. Okay, this gives us answer is minus 1 comma 2. What? I don't know, but the idea is the same. Like if you negate a vector and then add it with itself, you should get a zero vector, right? So I'm trying to do this and then multiply the vector with a zero vector. You should get a zero. Fine. So answer will be minus 1 comma 2. Hmm. Okay, fine. Uh, yep, yeah, now it makes sense. What is that? Okay. So yeah, this is wrong. Let me explain what is happening here. So in the new vector space, so the problem says in the new vector space, you have a new zero vector, right? So let me call it zero hat, right? Zero and an arrow on top of it. Then in the new vector space, you have a new zero vector such that u1, u2 plus this operator and minus u1 minus u2 should be equals to that new zero hat vector. And we don't know what is that new zero hat vector. But let's say if we are doing scalar vector product, then we all know that if you take a scalar 0 and multiply a vector with that scalar, you will get 0, right? So this 0 is known. This 0 is known. So you can do this. And then when you do this, you see that 0 vector is essentially minus 1 comma 2. Now let's try to put it there and let's see what happens. Let's try to find the negation of this vector, right? So something, so let's say v1, v2, such that v1, v2 is equals to minus u1, u2, right? Negation of u1, u2, which is essentially, this looks like in our well-known vector space. In this new space, it will look like this. Zero cap uh, plus new plus operator, and then apply the negation on this, right? So this will be the negative operator, right? And then from here, you can always find v1, v2. What is the additive inverse that makes it zero, right? So yeah, then zero vector is known. So just do this minus 1, 2 plus minus u1 minus u2, right? It doesn't matter because the only thing we know is that zero vector is unknown. But we always know that zero scalar is known, and multiplying any vector with zero scalar should give you zero. This gives us your zero vector, right? And this gives us zero vector has to be minus 1 comma 2. So option B is correct, right? Any doubt in this problem? Fine. So let's move on to the next question. So, so yeah. Hmm. So consider the vector space R2. Fine. We are dealing with vector spaces. Let omega 1 comma omega 2 be two subsets. So they are basically subsets of R2, where so there is some definition. Omega 1 says it is a vector that looks like x comma y, such that X into Y should be positive. Fine. So let's do this. Let's try to see on the Cartesian plane what it looks like, right? So it says X into Y should be positive. So basically this region and this region, fine. And omega 2 says X into Y should be negative. So that will be this region and this region, right? So this is omega 2, this is omega 1, this is omega 2, right? The question is, hmm, are they subspaces? So for subspace of a vector space, what are the properties that we need? So these all 10 properties should be followed, right? Zero should exist. There some should be a vector space belong to the same space, scalar product, and all these 10 properties, right? From there, we can examine whether are they, we just have to find one property that is being violated, or we have to prove that all the properties are satisfied. Then only we can say that this is the subset. This is a vector space, right? So first, let's talk about omega 1, right? So let's take a vector in this omega 1 region that looks like, let's say, mm, hmm. So let's take a vector 1 comma 1 and take a vector 2 comma 2, right? And yeah, let's
We
take a
can take
vector.
from third quadrant. So
No, let's take this only, right? 1 comma,
one in the first quadrant and one in the second quadrant. So I don't think that it will lie in the both omega 1 if you are going to add both.
yeah, right. Yes, you're right. So minus 2, minus 2. Let's take these two. Let's add this up. You will get minus 1 comma 1, right? Now this does not belong to it. It does not belongs to omega 1, right? So omega 1 is not a subspace. Similarly, for omega 2, we can check this out, right? So do the same thing. You take the vector minus, so what is the probability? Less than 0, right? Huh. So minus 1, 1, and then take 2, and then minus, minus 1. Let's take it to be minus, oh, sorry. Let's take it to be minus 3 or something, right? And take it to be minus 2. Yeah. So then add them up, you get minus 1, minus 1. So this does not belongs to omega 2. So omega 2 is also so not a subspace. Fine. So the answer is both are not subspaces of R2. Fine. Okay. Let's on to the next question. First question, first part. There are two statements in this problem. Statement one says every vector space is a
Excuse me,
subspace of.
sir.
Yeah.
Excuse me, sir. Like
Yeah.
I think more options are there. No? We have to check which option is correct. I think we have done only first one option,
In
previous
the
one
previous
question.
problem.
Yeah, yeah.
Ah, so,
We have
yeah,
done the.
yeah.
Okay, we
It
can check
says,
the all. Both are not.
yeah,
We have got the answer.
yeah.
Okay, I thought we are just checking the first one. Got it, sir.
No.
The- uh,
So all
okay,
the
second
options are
option is correct.
related.
Uh,
Hmm.
uh, got it. Thank you, sir.
Let's move on to question number 6, right? Every vector space is a statement one says every vector space is a subspace of itself. Is it true? Anyone? So,
First one statement is true. I think every vector space will be subspace of itself. That is correct.
hmm, fine. Why?
I think it satisfies all the properties now because it itself is a vector space.
That's fine. So basically, if you take a vector A, then you can always define its subsets as the null vector, sum of its subset, and the vector A itself, right? So now since A itself is a vector space and A is also its subset, then A will also be a subspace. So basically, yeah, it's a subspace of itself. Then every subspace of a vector space is a vector space. Is this true?
Yes, every subspace will be definitely will be vector space, I think, because it is a part. No, it satisfies the all
Yeah,
the properties.
right. So this is also true. Both statements are true. Right. So let's move on to the next question. There exists, so consider the following statements. Plot statement one, there exists a set of 7 vectors that span R10. What is the answer? Let's think of this problem, right? So let's boil down to the easier cases that we can visualize. Fine. So let's say I am dealing with R3 space and I want to span the R3 space, right? I want to span R3 space. So for sure we will need vectors that belongs to R3, right? And let's say I am saying I have only one vector that belongs to R3. So the question is, does V1 span R3? Take an example. Let's say V1 is equals to 1, 1, 1. And can you find a vector in R3 such that uh, linear not transformation, linear combination combination of V1 is not does not reaches the vector V. Can you? So let me take another example, 210. Can you scale V1 to get here,
No, no.
right? Now let's say
Mm,
if I have two vectors, V1 and V2, that looks like this. V1 is 1, 0, 0. V2 is 0, 1, 0. So are they spanning R3? The question is, are they spanning R3? And by span,
no.
what I mean, we should be able to reach all the
To reach
vectors
every
present in
vector.
the R3 space. Hello?
So
So
no,
by R3,
this will not.
yeah, right? So
By this,
basically all the vectors in the R3 space should be accessible from the linear combination of these two vectors. So I have an example where it won't work for V equals to 0, 0, 1. No linear combination will work, right? So now let's say if we have three vectors, V1, V2, V3, then may or may not, right? May or may not span R3, right? If you have three vectors, right? So basically, this is the idea. If you are trying to span n-dimensional space, you need to have at least n-dimensional linearly independent vectors. Otherwise, you won't be able to span the entire space. So the first statement says there exists a set of 7 vectors that span R10. That is not possible, right? In any case, you need at least 10, and then you check if they are linearly independent or not, right? Independent or not. So this is so wrong. Statement one is wrong. Statement two says there exists a set of 10 vectors that span R7. Now you have 10 vectors, right? That that may or may not span R7, right? The answer is, it says there exists at least a set. Yeah, that's true. One set at least exists. We all know that the R7 space can be spanned using some orthonormal 7 vectors in R7 space. So, and if you have already 10 vectors, out of them, 7 can be linearly independent. So you can span. So statement two is true. Do you have any doubts in this?
No, I don't have the doubt here. Like, but sir, one question is there. Like, if two vectors are independent, like
Hmm.
two vectors V1 and V2 are independent vectors. So
Hmm.
someone has like we are discussing. So one has told that if you are going to add zero vector in that, So it will become linearly dependent.
What zero is with what you're saying?
See,
I don't get the problem.
means ki if two vectors are given, like suppose
Hmm.
v1 and v2 vector, they are
Hmm.
linearly independent.
Okay.
So if I'm going to add zero vector in this v1, v1, v2, and one null vector, if I'm going to add, now it will
Okay.
form linearly that they will form linear dependent vector.
No. Why they should?
Because they are saying ki like linear independent means ki like suppose alpha x1 vector plus beta x2 vector will be equal to 0 if and only if like alpha and beta both are 0. It will be linearly independent.
Ah, then only. Yeah, right.
Uh, Now if you are going to add the 0 vector, so
Hmm.
they are saying ki 0 into any number again will be like if I'm going to add 0 on the left side vector,
Hmm.
like alpha x1 vector plus beta x2 vector plus they are saying ki gamma 0 vector will be equal to 0 vector. Now gamma
Then
we can take any.
gamma need not be zero, right?
So they are saying now it will be linearly dependent now these vectors. Means now means ki any two linearly independent set we can make it dependent by adding 0 vector. They are saying something like that. That I was
I
not
think this
getting.
violates the basic definition of linear independence.
Mm-hmm.
Yeah, this violates the definition of linear independence, right?
So they are saying from here we can now extend this part. Something what they are explaining. I was not getting this part actually. So
Where it was explained?
someone was discussing in my class, no? So one student was there,
Acha.
teacher means one teacher was there, so they were explain telling. So I've said no by because what we have studied, like if it is a linearly independent, so there we are going to get the solutions. Like we are able to reach any vector. I think linearly dependent independent vector that only we have studied. By from the set of linearly independent, we can reach I think any by linear combination we can
Hmm.
reach any value. So this part
Yeah.
we have not studied, or this I was not getting. I don't know, but okay, now this only a little bit, and one more little bit doubt was there
Basically,
from
the
the
definition of linear independence is if you have linearly independent vectors, then you can get you can span the space entirely.
uh,
But
uh,
like
if
it's if then else like kind of thing. If
hmm,
linearly independent, then span,
uh, this
right?
only I was telling. And
Yeah.
one more thing is there, like sir, like when we are solving the system of the equations, like
Hmm.
suppose it is not a square matrix now, like if
Hmm.
it is m cross n something, so I think the for such a system of equation we have a column space, and one is your null space, then row
Hmm.
space, and left null space.
Hmm.
So means ki call it when we are trying to solve the column space, it
Hmm.
means ki we are taking the particular input, we are dealing with the input cases, ki what are the particular inputs are possible, or we are seeing the output part. And for the null space, so I think null space defines the repetition of the data or something like that it is.
Null space is essentially related to the domain, right? So when
Uh,
you do matrix vector product, right?
mhm, mhm,
So you have some domain and you have some range, right? It's
mhm,
a mapping from its
mhm,
domain to range. And
mhm.
then null space is defined in the domain itself. Null space belong to this space.
It means ki null space says ki the repetition of the data. What they are saying ki redundancy, something like that. They are saying
Like who
redundant
is saying and what they are saying? What is
somewhere.
the complete statement?
Redundant means ki one of the suppose the vector is a linearly dependent, like one of the equation comes out to one of the vector will be linearly dependent, something like that it comes out to be. So redundant data, something like it was there in book
No,
something.
this is we have seen, right? You can have multiple solutions to these kind of matrices where there is some null space present.
Null space will be in the in the input zone only,
Null
means ki
space is
domain.
completely defined in the domain. because
domain
the
and
range of
column
the null space set of all the vectors in null space will
and
map to a zero vector, right?
oh, and column space will be in the range, no?
Range space, right? It's range basically.
That's why we find range. And row space will be,
Simply transpose, you take the transpose of the matrix, and then again there
it
will
will
be
be
a
in the
domain
domain.
for that, and then
It will be
the row space will be in the range, but it will be in the range of A transpose.
row space is also in the range.
In the range of A transpose. Now A and A transpose are completely different matrices.
Okay. Within the range, maybe within the range only.
Yeah.
But like range, range doesn't matters with the rank of the matrix, no? That is different thing. That will be different. This I'm getting.
The rank
And
of the
that
matrix is essential. Yeah. Hello. Yeah.
yes, sir, getting rank is the number of linearly independent vectors will be
Column
there.
vectors. A linearly
Uh-huh.
independent column or row vectors.
Mhm. And left null space will be again in which one part? Domain or this one range?
Again, null space
Left.
is completely belongs to the domain. You are
uh,
confusing few things, right?
No,
Null
no.
space is defined in the domain. Now, what is left null space? Left null space is associated with the column space, and right null space is associated with the row space, right? Now,
Okay.
what happens? There
Mm.
are two separate kind of matrices. One is A and one is A transpose, right?
Yes,
The
yes.
column space, row space for A is the column space for A transpose. Do you agree with this?
Yes, sir. Yes, sir.
The row space of A is essentially the column space of A. By that, what I'm meaning, I'm saying all the linear combination of rows of A.
Mm-hmm.
Okay,
Mm.
right. So that will be row space. Now, what happens generally is what actually happens. Let's see. So now let's say I have a matrix of dimensionality 3 cross 2, and then it maps from R2 to R3, right? Fine.
Mm. Okay.
Now let's look at A transpose will be 2 by 3, and it maps from R3 to R2, right?
Mm.
Now the R3 space is universal. It's a general space, right?
Yes, sir.
And A is mapping, A is basically mapping the range space of A is in R3, and the range space of A transpose in R2. Now, if null space of A lies in R2, right? I'm saying a null space belongs in R2, right?
Okay, sir.
Do you agree?
Got it.
Right?
Yes, sir. Yes.
Now, since this belongs to R2, so this belongs to R2, then this essentially means that you can always say that null space of A belongs to column space of A transpose. Do you agree with this? So let's say I have a set that looks like this: 0, 1, 2, 3, up to 100, right? Now I'm saying I can always say, right, one is a subset. Let's say call this set as A. So one is a subset of A. One is a subset of A. I can always say that two is a subset of A, right? Now R2 is a set. All the vectors present in R2 form a set, right? Now
Yes.
from that R2 set, right? From that R2 set, so let's say this is a set of R2 vectors. Then we are saying null space of A belongs to R2. So this is a null space of A, right? We are also saying range or row space of A belongs to R2. Let's call that RA, right? Right. So that also belongs to into R2, right? This is RA. RA transpose basically. RA transpose, right? Now, these may or may not intersect. That cannot we cannot comment on that. But that is essentially what they are saying. They are saying that null space of A belongs to the row space of A or column space of A transpose. That is what it means. Is this clear?
Got it. Got it, sir. Thank you, sir. This one.
Basically, this is the R2 space. Now, you can always see that the input here is output space. The output space here is input space here. So that's why this kind of confusion arises. Like is the null space in the row space or it is not in the row space. But column space and row spaces are uh, not exactly same like this basically.
What I was just searching the application of that. So there
Hmm.
it was saying ki column space mostly is for the outputs, that what corresponding outputs you are going to get, that
Hmm.
defines the column space.
Hmm.
Then it was saying ki null space states that the repetition of the data, like redundant data, like one of the vector is the linear combination of another one, means one of the row will maybe the linear combination of other, means there is a repetition, so that there we are going to get the null space, I think. That's why the null space they are also saying ki it is in the input range only.
So let's say, yeah, null space is always in the input
Yeah,
space,
so
domain
that part
space.
they was explaining. That was,
Hmm.
and row space they were saying ki when we are taking the input, so it keeps the check on that there ki the user should not enter the wrong input data, like for the row space. So row wise, that is also for the input space. For input only they are saying for the row space. It keeps the check whether the all the inputs are correct or not. Something that.
Okay. Which application you are talking about?
Like for the data feeding or for reading the data or something. I think for the data science type, like any information we have kept in the form of the matrices, like
Hmm.
suppose we have made a 10 cross 15 columns, and there we
Hmm.
want to get the something from their result. Now they are saying ki from this one, what you are going to get the details from this data,
Hmm.
that will be in the column space, and the repetition of the datas will be in the that will be defined by the null space, like particular properties are repeating, which is not going to affect the output part. That's why it is, I think, mapped to 0. So that keeps the check on the repetition of the data. And row space is saying ki each row the entries should be correct. If it is not correct, means ki that defines on the row space, something like that. It has been explained, I think.
I think you need to think
Uh,
either give me some reference to this or you may go back and read it
okay, okay.
in detail, right?
Okay. Next time I'll share that one part if somewhere I'll get that part. Yes, sir.
So let's move on to the next question. Consider the following subspace of R4. So basically, we are dealing with R4, and all the vectors in this space, subspace, are defined like this, which is a set of four scalars, right? U3, U4, such that for all I, so basically U1 plus U2 plus U3 plus U4 is equals to 0. The question is, what is the dimensionality of U, right? So what is the dimensionality of a space, of a subspace? So dimensionality, we already saw this, right? So a dimensionality essentially means what is the number of vectors that span that space, right? Uh, so dimensionality essentially means number of vectors that span that space, right? So now, can we comment on the dimensionality of this space? So the properties that these scalars hold are u1 plus u2 plus u3 plus u4 is equals to 0, right?
So one of the vector will be the linear combination of other.
These are
Now,
scalars. These are scalar quantities. These are
okay,
not
okay.
vectors, right? U1, comma U2, comma U3, comma U4 scalars, right? So what you can see that here is one of the scalar can be written as a as a sum of other scalars, right? Am I right here?
Yes, this we can write. I think we can replace that one part.
right? So basically, you essentially don't need the value of u1. U1 is not at all required. So the only variables that we are interested that will define this space is u2, u3, and u4. And the question is, if you have three scalars which are independent, then how many dimensions can we span? The question is how many. This is quite clear, from right? This is clear, right? You have three scalars.
Yeah, yeah.
You
Three,
can
three.
always span the R3 space, right? So this
Mm-hmm.
is R3, right? That's fine. So let's move on to the next question. Which of the following is not defined the property of vector space defined over a set of real numbers? Okay. For any two vectors in the vector space, the vector has to be an element, right? Fine. But one has to be true always. For the property two,
Second
it
also true.
says every vector in vector space, there exists a negation vector such that u plus u equals to 0, u plus minus u equals to 0. Then for every vector in the vector space, there exists u inverse such that u into u
False,
inverse
false,
equals to
false, false, false.
1. And then last one is alpha u is an element of ub, right?
Third
So
one is
options,
false.
yeah, option C is false, right? Fine, because in vector spaces, inverse of division is not defined.
Yes, sir.
Basically, there are only two operations: addition over vectors and scalar product. So this is involving vector product, right? Vector vector product, which is not defined actually.
Uh, like one question, like inverse may be there in the vector space, may not be there. No, that statement will be true. Means ki any vector space is there. Like so,
Hmm.
if you are going to take any vector in the vector space, so
Hmm.
the inverse of the that vector may be there or may not be there in that. It can be also possible. Like for every to it is wrong, but for some of the vector may be present, for may not be present, because there are some matrix whose inverse I think a inverse is equal to a also is possible, no? Sometimes
Right. Uh,
a inverse
um.
equal to a, because a square equal to I, if such matrices, if I'm going to get a square equal to I, means ki it means ki uh, inverse of the matrix is the matrix itself. First,
Right. But yeah. But the vector spaces only contain these two operations, right?
means that I'm saying ki inverse we don't have to go with the inverse multiplication and something like that, because that property we are not taking. So
Hmm.
it may be ki inverse of the matrix may be present by chance, because the
We are
matrix
dealing with
itself is the
vector
inverse.
spaces, right? We are not dealing
Huh,
with
huh.
matrices here, right?
So I'm saying that only part ki, okay, in the vector space, like if, whatever the vectors are formed, if it is a square matrix, like so it
So,
may
so
form, no?
these are all 10 properties of a vector space,
Okay, okay.
right?
This I've
So
understood. C property
you
means
only
ki
have
C
to
will be
look for
false.
these properties,
Okay,
right?
okay,
So
okay, okay,
the
okay.
operations are only defined as addition with a vector and scalar product. That's it. Fine. Is this
Got
clear?
it, sir.
Yeah.
But it was clear that.
So let's move on to question number 10. Let S equals to U to U3 U be set of non-zero vectors in I3. In R3, the s- okay, yeah. So the span of S is, right. So you have vectors U, 2U, and 3U, right? So what is the span of this vector? So let's say this is a vector representing this vector, and u is basically a scaling factor. So let's take the vector 1, 2, 3 multiplied by u. So let's say this is your vector 1, 2, 3, and then you can scale it in all the directions. So what is the span of this? A line, obviously.
To
So
the
it's not a
line
plane
passing
because
through the
you're
origin.
dealing having only one vector, and when u equals to 0, it passes through the origin, right? So option A is correct. Is this clear?
Yes, sir.
So number of linearly independent vectors that span a 13-dimensional subspace of a 20-dimensional vector space is the answer. So we are talking about linearly independent vectors uh, that span a 13-dimensional space in a subspace of 20-dimensional vector space. So this, again, you can go back to the basics. So let's say you have a 3-dimensional space, right? And you want to span 2D space. So how many linearly independent vectors you need? Huh? So let's say I want
For
to span the XY plane. How many linearly independent 3-dimensional vectors you need?
in two, I think two we want for by
Right?
two, no? Mm.
Yeah. Why?
Um, because by two linearly independent, we can reach any point in the that part, no?
Right. And similarly for 13-dimensional space, how many you need?
We need 12 for 13,
Why
no?
12? Why 12?
No, no, 13 dimensional. To get the 13, we need 12 independent, I think.
Why? Let's say if
12,
you want to
no,
span 2D space, then you need a line or you need two vectors.
we need a line.
For 2D,
Uh,
you just need a line,
for two dimension, I think no. Two dimension, we need two dimension only. Then only we can reach, no, two vectors.
right? So you
Because
it won't work if you only choose one vector, right?
right, uh, for two
Let's say,
dimension we need two.
right, for 2D, similarly for 13 dimension, we need 13 vectors, right? Is this clear? I'm just extending the
Yes,
properties from 3D,
yes.
2D to
Oh,
13 dimension and 20
mm,
dimension, right?
got it.
So basically, let's say I want to span the XY plane, but I have vectors in R3 space. So the vectors 1, 0, 0 and 0, 1, 0, these two are sufficient to span the 2D space. But if I choose only 1, 0, 0, you won't be able to span all the R2 space, right? Is this clear?
Yes, sir. Like
Fine.
what you have taken, like two vectors. Like if you take two vectors, so with that we can reach in the three dimension, no?
How?
Two li- two linearly independent vectors, we can't reach three dimensional.
How can we?
Like
Let's say I
like
want to reach the vector 0, 0, 1. How can we?
okay, it is in 3D by huh,
What linear combination of these two will give us 0, 0, 1?
okay. This is the special. Like I was just thinking ki any two vectors will take, so we'll be able to, that is possible in the I think 2D case only, no? By if we are taking two linearly independent vectors,
Hmm.
so we can reach any vector in the two dimensional space only,
Ah,
not in the
fine.
three
Yeah.
dimension.
How you
So if
can't, right?
hmm, okay, so for 3D space, for 3D, we want three linearly independent means
Yes, the definition of dimensionality is the number of linearly independent vectors
independent
required to span
vectors.
that
Okay, got it.
space, right?
Got it. Previously also we have done this topic, no? And I think just now before that also. Thank you, sir. Got it.
Okay. So let M2 cross 2 denote the set of all 2 cross 2 real matrices. Let S be the set of all real 2 cross 2 singular matrices. Let R denote the set of our invertible 2 cross 2 matrices. Fine. Then the question is, S is a vector space over R and okay. Hmm. Statement 2 is R is a vector space over R. Okay, fine. So let's proceed this. So we are dealing with vector space over R, right? And let's talk about S. S contains all the matrices in the dimension 2 by 2 matrices, right? So, and by vector space over R means, let's say if we do this either addition or scalar product operations over vectors matrices in R2 cross 2, can you span the R1 space? The question is this. Can you? And you're only allowed to
Like
use 2 by 2
any vector in
matrices.
the subspace,
Yeah.
scalar multiplication again, it will be singular itself. I think.
No, no. What I'm saying is, let's say I have a matrix A, B, C, D, and I have a matrix E, F, G, H. Now, either you do add these two or you multiply some scalar with this into some scalar. Is the result something you will get some result? Does this belongs to R1? The question is this. Does this belongs to R1? No, right?
No.
Right? Because it will be a matrix and this will also be a matrix, right? Am I right?
Yes, sir.
Is this clear?
Yes, sir.
So
Yes, sir.
these were the problems from week 2, week 8, right? Now let me have a break of 5 minutes and then we can start with the problems for the next week. Fine. So hi everyone. So let's resume the session, right? So in the last problem itself, yeah. So yeah, we finished this problem, right? So let's uh okay, fine. So the meaning of this over R, yeah, right? Earlier what I earlier what I thought was something different, but yeah. So this essentially says that the matrix input domain is R, right? So the domain is R. Basically, all its entries are in R space, R1 space, right? Now the question says, am I audible?
Yes, sir.
Yeah. So the question says, now let's say we want to check if the if these two kind of sets belong are for do form us do satisfy the vector space properties. So basically, we are defining some operations over these structures, right? And the operations are plus and scalar product. And the property of all the 10 properties that we have seen should satisfy, then they belong to a vector space that satisfy the vector space, right? So the first set is S is essentially singular vectors, singular matrices, right? So the property, let's check the closure property, right? Now let's say if we have a matrix that is singular, that looks like this, right? And then another matrix that looks like this. And these both are singular. So when you add them up, their closure should be also a singular matrix. But you see the summation is not a singular matrix, right? So it's not closed under addition. Closed under addition. So it's not a vector space. Now again, R is all invertible matrices, right? Invertible matrices. Now let's check again the closure property over addition. So let's choose this matrix 1 0 0 1, right? And then take this matrix 0 0. Sorry. Yeah, 0 1. Okay, what can I form here? Hmm.
0 0 -1 also we can take.
0 minus 1. These two are invertible, right? Now the sum is basically 0 0 0 0, which is also singular, right? So this is also not closed under addition, right? Am I right?
Yes, sir.
Right. So both are false. Fine. So this is done. Okay, I have just simply. Oh, question 12 and 13 are same. Okay, fine. Yeah, question 12 was copied twice. Yeah, so that's it for week 8. Let's finish up the week 9 problems very quickly. Which of the following matrices have its null space and the column space to be the same? So basically what this means is so let's try to figure out the null space first. So we have the matrix 0 1 0 0. So what is the null space of this matrix? So you have to find vectors as that A, V1, V2. V1, V2 are scalars. So this matrix is defined over R1 has to be 0, right? This says V2 has to be 0. And this means any matrix that looks like this, any vector that looks like this belongs to null space of this matrix, right? Do you agree with this? How I have
Yes,
found
sir.
the I how did I find
Yes.
the null
Yeah, yeah.
space?
Got
Fine,
it. Yes, sir.
fine. Now, so this is a 0 0, right? So, right. Now, what is the column span of this matrix? Column span is, so what is the column space? Basically, linear combination of the column vectors. So alpha into 0, 0 plus beta into 1, 0, which is essentially beta comma 0, right? Now this is the column space. And can you see that these both are same things, same spaces, right?
Yes, it is same.
Right, right. So this has the same column space and the null spaces. Let's check the another matrix 0, 0, 0, 1. Now again try to find the null space. You will find that 0 comma u2 will be the null space. And then again linear combination will be right. U1, am I right? Huh.
Yes,
Fine.
now the column space we have to check.
Hmm. So now the column space will be alpha 0, 0 plus beta 0, 1 is 0 beta, right? These both are same, right?
Hmm.
So similarly, you can check all the matrices. Check this for all the matrices, right?
Question was which one is not? What is written? Not.
No, it has a null
Question
space.
be same. So it can't be multiple choice then, because option one is also correct and option two is also coming correct, I think.
Option 3 will also be correct. No, option 3
So
won't be correct.
because so it is not a multiple choice correct. Means ki many options are not correct, no? Like
Oh,
any
sorry,
one will be
sorry, sorry,
correct.
sorry. I did some mistake here, right? I did some mistake here. This says U2 has to be 0. So this will be, that's what I, U1, U comma 0 will be the null space and this will be the column space, right? There was a mistake in computing the null space,
It is correct. Now it is correct.
right? Okay.
Right. Option
So
one is
only
correct.
option A1 you will get this. Option 3 also you will see that the null space would be 0 comma x, right? And the column space will be alpha comma 0. Again, these are not same. For option D, you don't have a null space. So basically null space is empty set and column space obviously is alpha comma beta, right? So they are not same. Option A is correct. Fine, is this clear?
Yes, sir.
Question 2 was covered in the previous lecture itself. Move on to question number 3. Suppose A is a matrix of size 5 comma 8. Fine. So we have 5 cross 8 matrix. It's a full rank because rank is 5, right? Then which of the following is always true? Ax equals to B has infinite solutions, right? A is 5 comma 8. B has to belongs to R5, right? So A belongs to R5 cross 8. X belongs to R8 and B belongs to R5, right? Now the question is Ax equals to B has infinite solutions. Hmm. Null space of A is 5-dimensional space. The null space of A is 3-dimensional space. It has unique solution for every B belongs to R8. Right. So what should be the answer? First of all, null space of A is basically 3-dimensional space of R8, not R5. Right? Is this clear? Option C, why it's wrong? Fine.
Yes.
So now let's talk about the number of solutions, right? So A has 5 rows and 8 columns, right? So how will it look like?
Uh, sir, we can proceed like this also. I think so. Like if it
Yeah.
is 5 cross 8, so
Hmm.
yeah, it is mapped in R5. I think total uh, dimension will be R5
Hmm.
output, because
Yeah.
column space will be mapped in R5.
Hmm.
Okay. So what will be the rank nullity theorem can we apply here? What will be the null space in this case?
Three-dimensional subspace of R3, R8.
R8. So, like, if we apply like rank
So
and rank
look
penalty
it
theorem.
like this. So try to look it like this. You have five equations, right? And eight unknowns, right?
Yes.
So this is underdetermined system of equations, right? What happens in these scenarios?
Maybe no solution or infinite many solution. We are going to get two situation underdetermined.
Okay, so let's check this out. X plus.
Like total solution will be like particular solution plus whatever the null space is going to give the contribution. So if the null space is going to give the only zero solution, like trivial solution is there, null space, then so unique solution will be there. But I think it is underdetermined, so only two cases will be possible for underdetermined. Let's take like three variable and we can check it out like what we are going to get. It has only two options. I think unique solution to underdetermined will not come.
Yeah, right. But the thing is, since it is underdetermined, right? Um, you actually will get, you cannot get the actual solution. You will get multiple solution that will project onto same points, right?
So infinite many solution will be there
Yeah.
because but sometimes underdetermined maybe no solution is also possible. I think so. This two underdetermined two cases are there.
Okay, think of it like this, right? So you have eight columns here, summation alpha I, column I, right? I goes from 1 to 8, and the eight columns and each column of dimensionality R5, right? So you have eight vectors in R5, right? You have eight vectors in R5, and then you want to find the coefficients of these eight vectors, right? Such that AX equals to B. Fine. So this essentially means, let's say I have this kind of setup. So let's take a simple 3x2 matrix. Let's not go into this. Sorry, 2x3 matrix, right? That we already saw here, right? 2x3 matrix here. So let's write this up, right? There's 2x3 case here. Uh, So you have this matrix that looks like one. Okay, so this is 3x2, right? 1, 2, 3. Right. This was 3x2 case, right? The case was wrong. So let's do this for smaller case and then we can extend from there, right? So let us take this x plus 2y is equals to 4. Fine. But the number of number of the rows has to be less than the number of columns, right? It was right case. X plus 2y plus okay, so you will write xy here and then you will write the coefficients, right? And then you can always change the number of this into this into this. So you can have 1, 2, 3, 4, 5, 6, right? Something like this. So this is a 2 cross 3 matrix and, oh, sorry, a 3 cross 2. This is the case we were trying to look. No, we are trying to look 2 cross 3 case, right? 2 cross 3. So 1, 2, 3, 1, something like this. And then X, Y, Z. Then this is 2 cross 3, and this is 3 cross 1. And this is mapping to some B, B2, B3. That is again to B1, B2, right? B1, B2, which is 2 cross 1. Fine. So this says X into 1, 3 plus Y into 2, 4 plus Z into 3, 1, right? Is equals to B1, B2. Now my question is, can you write 3, 1 as some linear combination of 1, 3 and 2, 4? Can you? So then, can you do this?
Hmm.
Right?
I think it is not.
Because these two are linearly independent, so they will span all the two-dimensional space. So you can
Um,
always write this, right?
all
You
right,
can
this
always
one,
get
yes,
this
sir.
alpha.
Mm-hmm.
So simply just replace this 3, 1 with alpha into 1, 3 plus beta into 2, 4. Now, when you see the system of equations, you will see that x into this plus y into this plus some alpha beta, right? Right?
Yes.
Now, from here, what you can just think of it is, from here, what you can think is, you see that x into 1, 3 plus y into 2, 4 plus z into alpha 1, 3. Okay, let's say. So this will become x plus z, f plus alpha z into 1, 3 plus y plus beta z into 2, 4 is equals to beta 1, beta 2, right? Now this will tell you that, so x, y, z, everything is a scalar. So this will give you x plus z alpha. So basically from here, what I'm trying to say
Like,
is,
okay.
hmm,
Like, we can convert in RREF form also, no? By that
hmm,
also we
hmm,
can clearly see that part, no?
hmm.
Can
So
we
basically I'm saying
do that?
is, depending on the choice of alpha and beta, you can have multiple solutions for this equation, right? Right?
So, it has infinite many solutions. That only I was saying,
Yeah,
like,
yeah.
underdetermined to cannot be unique solution.
There can't be unique solution.
Mhm. So, but some cases may arise like underdetermined may not have solution. That case also
Meaning?
may arise. I think so, because for underdetermined, that case may come. No solution may
Yeah, right.
exist.
So basically the matrix is full rank, right?
If it is full rank matrix, so there will be infinite many solution.
Right. And the question says that the matrix is full rank. So it says it's a matrix with rank 5. This means it's a full rank, right? Fine.
Yes, sir.
So basically what you have to think of it like this. So it's very unusual way, but you can look at like this. So let's say you have vectors in R5 and you have 8 such vectors, 8 vectors in R5 such that 5 are linearly independent, right? What this means, you
By this
span
combination, we can, yes.
the R5 space. Now, this means that AX equals to B has at least one solution. And since this is underdependented, it says it has infinite many solutions. No solution case never arises for this case. Fine. Can you proceed to the next problem?
Yes, sir.
So there exists no 2 cross 2 real matrix such that whose column space is the zero dimensional subspace, that is the subspace that contains 0 comma 0 only. Uh, okay, so let's check the statement one's claim and then we'll proceed with statement two. So it says there is no 2 by 2 real matrix, basically matrix with real scalar entries, whose column space is the zero dimensional subspace 0, 0, right? So basically, let's say if you have some matrix like this, A, B, C, D, and you have some vector X, Y, right? So the column space will be the vector X into AB, AC, plus Y into BD, right? So this spans the column space. The question is, there is no matrix such that the only solution to this is the only space is 0 comma 0, right?
Mhm.
So this is there is no such matrix. Can you tell me some matrix? Can you give us some contradiction to this statement? Can you think of this matrix? The 0, 0 matrix for any x for all x and y. Is this clear? So then, am I
Yes, sir.
audible?
Yeah,
Fine,
yeah.
right? Then again, there is no 2 by 2 real matrix whose null space is entire R2. The null space is entire R2, right? Again, in this case, you can see this 0, 0 matrix, right? Now, what is the definition of null space? Ax equals to 0, such that x is a non-zero vector, right?
Yes, sir.
Right. So both the statements are false. Option C. Any doubts in this?
No, sir.
Fine. Let A be a signed by 8 matrix. If the nullity is 3, then the nullity of A transpose is. So let's again draw that figure. A is the input is AR8 and it maps to R7. And then let's figure out the similar thing for the A transpose, right? It maps from R7 to R8, right? Then what is the rank of this matrix if it is a full rank matrix? Can you tell me?
Oh, 7.
Right. Right. But the question is nullity of 3A is 3, then what is the nullity of A transpose, right? So let's use the rank nullity theorem here. Let me move this here. Hmm. What does rank nullity theorem says?
Uh, Dimension of column space plus null space will be m m like 8. It comes out to be 8.
Basically, NA, let's call it NA, and then
Rank,
RA.
rank.
RA is the rank,
Sorry.
is essentially equals to the column, right? Number of columns. Fine. So the question says the nullity is 3. Basically, dimensionality of NA is 3. So put 3 here. Plus RA is equals to 8. This means rank of A is 5, right?
5.
Now put this here.
Now the
The same.
for the column, uh, dimension of the column and n transpose, I think A transpose. Okay, from here only we can find, I think.
Yeah, so
Now
rank of A transpose is equals to number of columns is 7 here. And we know that rank of A is equals to rank of A transpose, which is basically 5 here, right? Am I right here?
5 2, it comes out to be 2.
Yeah. So option C is correct. Fine.
Yes, sir.
Any doubts?
No, no.
So I think we have 5, 6 more questions for week 9, but I will cover them up in the next session. That's what I'm thinking on right now. I want to give a brief introduction on the topics covered in the week 10. Fine. Is that fine with you?
Okay.
So, so let's start with the introduction on the topics. So, so we earlier we saw the system of equations, right? Mm. Right. So, yeah. So we saw the system of linear equations, right, in the very beginning of the lectures. So this is clear to you, right? System of linear equations and what is the definition of consistent system of equations, right? And how to solve the system of equations. Then what is the meaning of the solution? What is the column space of A, right? And then we saw that how to see if the system of equation is consistent or not. You can use RREF to find out, right? Okay, so the first thing that was taught here is what if the matrix is not a square matrix, then what you will do?
Two things like for the overdetermined equation and underdetermined equation. So how to come up with the like solution is possible or not? I think it has been not covered in the topics this time so far. Just now to week 10 video to I've not seen classes just now.
Okay, so week
So
10 is not released.
no, it is released. I have not gone through actually just now.
Okay, so then it would be better for if I solve the remaining week 9 problems, right?
Showing the basics that will be I think more proper. Like concepts will be developed now. You're just now you're showing no that's notes one. You're discussing just now
Yeah,
for
so
consistency and inconsistency. Let's
so
do
let's
that
say if
part.
you have a matrix that has dimensionality m cross n, the rank is RA and null space of is NA, right? These definitions are well known. The question is you have a system of equations AX equals to B. The thing is, do we have a solution for this system? right? So let's take an example here, 1 0 0 0 1 0, right? And let's take your x as xy and take your b as 1 1, right? Do we have a system of solution for this system of equations? So it says basically x is 0. It says simply x comma y is equals to 1 comma 1, right? So we have a unique solution here, right? Do you agree with this?
Uh, okay. Last you have added 0 0, no? If I'm not going to add 0 0, like last one you have added no 0 0. Third in the m cross n you have taken 0 0
Oh,
last.
yeah, the system is wrong here.
Okay.
So it
So if you take
says
some
x, y, and 0 is equals to 1 1 0, right? So this gives you x equals to 1, y equals to 1, right? As a solution.
like what I'm saying, like
Hmm.
in place of 0 0, if we take 0 2, then like in the a matrix what you have taken, so the first vector is
Hmm.
1 0 0 in the a1,
Hmm. Hmm.
second 1 0 0 0 1 2, let's take this one xy, and this
Hmm.
is going to give something.
2y, right? So there exists no solution here. Y has to be 1 and y has to be 0. This is not possible, right? Fine,
Yes, sir.
fine. But why this happened? What happened here? So why this happened? Like, how can we identify if a solution will exist or not? So let's say we have a set of vectors Z such that Z belongs to the null space of matrix A, right? Right? So now our
Yes,
matrix
sir.
was 1 0 0 0 1 2, right? So what is the null space of A? Let's define the null space. Let's try to find out the null space of this matrix. AB equals to 0. This gives us A 0 0 0, right? This gives us A, B, and 2B equals to 0 0 0.
uh, like what I was doing, like if it is written row wise, so one is I think
Hmm.
linearly dependent, so it is not better to
Basically, row 2 is linearly dependent on row 3, right?
hmm, 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 hmm.
So you can
So
always do this, use RREF to reduce this matrix first.
that only I'm saying.
So you reduce the matrix to basically use RREF to write it as 1 0 0 1 and 0 0 1 and 0 0, right?
What we have solved now, I think now we
And
have
basically says this is RREF. You are using the augmented matrix here. So augmented term was here 0 0 0, right? No, the null space is essentially 0 0 x. No, this is not 1 0 0 x. Right. This is not right way to do this, right? You define a some non-zero vector as v1, v2, and then you try to find the null space, right? 0 0 0. This gives you v1, and this into this will give you v2, and then this into this will give you 2v2. Now this has to be 0. So this is not v, but v cannot be 0, right? V cannot be a 0 vector. So this is not giving us the desired form we want. It's a full rank matrix, right? This is a full rank matrix.
yes.
Yeah, so you are only getting this. That's why you are getting only. Fine. So what was your doubt in your problem first? Satinder, why did we take this example? Can you explain? Okay, never mind. So let's ignore this example. This is not as useful as we wanted, right? Fine. So what actually I was trying to make sense from here is, so what actually I wanted to show you here is, so if you try to solve Ax equals to B, you are basically finding out the value of scalars such that x1 up to x1 such that B can be written xyz as the linear combination of columns of A. So if we can find such scalars, then B can be written as the linear combination. And we cannot find, then it cannot be written as the linear combination of the span of A, right? How do we know if given a system is consistent or not? Right? You can simply try to solve it and you will see if solution exists or does not exist, right? And this essentially brings us to this consistency criteria, which is, let's say we have this, right? Let's say we want to solve the system of equations Ax equals to B, then the solution will exist that will be consistent if and only if you take a vector in the null space of A transpose and then check if B dot null space vector has to be 0. This is the criteria that you see, right? Then only Ax equals to P will have a solution. How did we reach here? How did we define this consistency criteria? This you can simply work out by taking a general M cross N matrix and finding the pattern here. How are you reaching, right? So let's try to make sense of this.
I think above example has been solved. I think one
Yeah,
above
yeah,
one
for
it
that
has been
example.
solved.
Yeah. So basically, how to get to this idea is basically, let's do one thing. Let's think of the space P. This is the column space. So this is the column space of the matrix M, right? So all the vectors Ax equals to Ax map here. So all the vectors B. So B belongs to this space, right? Now, now what I'm saying is, let's say, now let's say I'm saying that I have an input vector X, right? And I take the solution Ax equals to B and try to solve this, right? So if X lies in this space, right? Then only you have the solution. Now, let's say if you have some vector that does not lie in the space, then it does not have a solution, right? Now, then it may or it may not have a solution. Then what the question is, when it will have a solution. When it will have a solution, the criteria is this consistency condition, right? So we can look at this example also, right? So for what values of B, we have the solution, right? So you fill up the RREF, create the RREF form, right? And for consistency, you need to see, you need to check that B3, B1 minus 2, B2 plus B3 has to be 0. Now you can always check, look at A transpose Y here. Uh, 1 minus 2, 1. Basically, what they are showing here is that for the consistency criteria, what you do, you find the null space of the matrix of A matrix transpose. So you find an A transpose and you check that if and B dot Y equals to 0, such that Y belongs to an A transpose. And this is they have done by seeing this example here. And they are saying that will this have a
Actually, this
solution or not?
NA transpose is the left null space, no?
Yeah, right. So from here, we know that RA transpose is perpendicular to NA, and then RA is perpendicular to NA transpose. So from here, you can build up this intuition here, right? Right, and then they are explaining this least squares idea. So I think we already saw this least squares stuff, right? So what is the least closest projection of a vector onto the range space of a matrix? How to get to the solution, right? Do you have any doubts in the least squares idea?
No, I think last to last class, I think you have explained that part.
So that was
Least
already
square solution
covered.
one.
So did I cover the pseudo inverse stuff?
Which one, sir?
Pseudo inverse?
No, 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 no.
Fine. So let's take on this topic in the next lecture, right? So if you have any other doubts, you can ask me right now. So let's proceed from it. I will basically cover up all the topics for week 10 in next week, and somewhere in middle of the next week, the schedule will be announced if I get to have the extra class, because actually we are lagging behind. So I wanted to take some extra class for this. So I think it will be scheduled in the next week. If it is, then we will finish cover these topics in that week class, right? So if you have any doubt, you can ask me right now.
Like I'm asking, like uh, for this one part, no, what is the applications where it will be used now? I think
What?
what we are doing, whatever the things we have covered, no. So
Mhm.
its applications, like where it is used, like how can you?
So, for example, if you talk about systems of equations, right? Um, how to give you an example? So let's say if you are trying to do some sort of polynomial curve fitting. So let's say I am saying my data fitting. Basically, it's very useful in data fitting, right? So let's say I have some data, some XY pairs, right? So this is X and this is Y, right? So we only know these discrete data points, right? And the question is, can we find a polynomial of degree 3, a polynomial of degree n, such that it passes through all these data points, right? So there is a problem of curve fitting, right? So let's say I am saying the points are 1 comma 1, and then 2 comma 8, and then 3 comma 27. The question is, can you find a curve, polynomial curve of degree 3 that passes through these 3 points? Can you? So this is 1 comma 1, this is 2 comma 8, and then 3 comma 27 will be somewhere here, right? So I can always define a polynomial curve as ax cubed plus bx squared plus cx plus d equals to 0, right? Okay, you actually need 4 data points for this. So 4 comma 64, right? Right. So now what I can say, I can always write this as x cubed, x squared, x t, right? And just repeat this here, x cubed, x squared, x and d, x cubed, x squared, x and d, x cubed, x squared, x and d, right? And then you put this a, b, c, d here, and then it says a x1 cube plus b x1 squared plus c x1. So this is x1, right? This is x2. Oh, sorry, this is 1. This will be 1, right? 1, 1, 1, 1. This is x3, and this is x4, right? Is equals to, now again, for x, so and your x1 is 1 here, x2 is 2, x3 is 3, and x4 is 4. And for those values, you get the b values as 1, 8, 27, and 64, right? Now simply put in the values of x1, x2, x3, and x4. You get this 4 by 4 matrix. It is essentially 1, 1, 1, 1, then 8, 4, 2, 1, then 27, 9, 3, 1, and 64, 16, 4, 1, right? And then you try to solve these systems of equations. A, B, C, D is equals to 1, 8, 27, 64. Can you tell me what will the answer for this system of equations?
A will be 1, I think so. B, C, D will be 0.
Right.
Because
So the solution is A equals to 1 and B equals to C equals to D equals to 0, right? So you get the solution as 0, 1, 0, 0, 0. Now, can I write the polynomial from here? This gives us the polynomial as y equals to 1 into x cubed plus 0 into x squared plus 0 into x plus 0 into 1, right? Which is equals to y equals to x cubed simply. Now we got a polynomial that actually approximates these data points, 4 data points, right? Which is y equals to x cubed, right? So these were your 4 data points, right? This was 1, 2, 3, 4, and you got a degree 3 polynomial from here by using this system of solving these systems of equations, right? So this is a kind of curve fitting that is very useful, right? So this is one of the applications that you will see. Fine. Is this clear?
yes, sir.
So basically here again, we are you trying to solve the linear systems of equations. Now, let's say this is all about the square matrices. Now, let's say if I am dealing with rectangular matrices, I have a data. Let's say I'm trying to build up a movie recommendation system, and I have a data of 4 users, A, B, C, and D. And then let's say we have some columns that define the properties of the movies. So let's say one is genre, right? One is like what we can say. What are the properties of a movie? Maybe language.
Which one property?
Let's say if you want to define some properties for a movie, language, genre, right, comedy, that kind of stuff, right? And then what other things? Like is it 18 plus or not? Something like this, right? Or any other property. Number of likes. Let's say these are the 4 properties. So let's say I am defining a movie one, right? One, and it contains 4 attributes. Genre is, let's say, comedy, language is English, and then it is 18 plus no, number of likes is 100, something like this, right? Can you fill up this kind of data?
Yes, that can be filled now.
Right. Now let's say user A has watched um, user A, what can we say? User A, let's say, what are the preferences of user A? He likes comedy movies in English, right? He doesn't like 18 plus movies, no. And then he likes movies with greater than likes greater than equals to 100, right? Similarly, B likes horror movies in Hindi, no. Likes greater than equals to 5 works. Similarly, C likes tragedies, let's say some other language, right? Other language. It no, and then less than greater than he requires at least 100. And similarly, he likes again comedy, English, let's say yes here, and greater than equals to 1,000, right? Now, can you transform all this? So let's say for genre, you have 4 genres, right? You have four genres. So you can assign a number to each of these, right? Comedy is 0, horror is 1, tragedy is 2, again comedy is 0, English is 0, Hindi is 1, other is 2, English is again 0, this is 0, 0, 0, 1. And let's divide this likes into ranges. So let's say greater than 100 is 1, greater than equals to 5 is 2, greater than 100 is 1, greater than 1000 is 3, right? So now you have a matrix that looks like this: 0, 1, 2, 0, 0, 1, 2, 0, 0, 0, 0, 1, again 1, 2, 1, 3, right? And you want to find right, you have this kind of matrix, and from this kind of matrix you want to find which movie is like most users with like which kind of movies, right? So then you will learn of some concept in future in the next class that we will see is eigenvalues, and they will help us to figure out something from this matrix properties. So essentially you try to quantify the data in forms of matrix and then see the properties of those matrices, right? Is this clear?
Yes, sir.
So
Like
this is essentially used in movie recommendation systems, this kind of
okay,
stuff.
okay. Like if when we are applying like ax equal to uh, b, like ax equal to b system of equation we are applying. So
Hmm.
b need not be a column matrix like what b we are getting. It may be also like uh, m cross n, like output also
It
vectors.
depends on X, right? If X is a vector, you won't get M cross n. If X is another
Okay.
matrix, you will get M cross n, right? This is basic matrix product.
Okay. So I think what just now you have explained your Instagram, Facebook, Reels, this
Hmm.
all, I think it works on this concept only, no?
I don't know what they actually use, but yeah, the basics are like
Because
similar to this.
because what they are watching so continuously, maybe it keeps and watch, and then continuously they are recommending that type of only videos like on that.
Yeah, right. But the basics are these, but right now what they are using, I'm not sure about.
Okay, Miss, I was thinking maybe the concept maybe using the linear algebra concept only they are maybe using. I've got
Yeah, right.
like, and sir, for that part also like what the uh, suppose government is keeping a record, like you have a Aadhaar
Hmm.
is linked with your uh, all the databases are there in that, no,
Yeah,
your address and everything, eye scanning and fingerprints. So maybe that also data will be stored in the form of
yeah,
matrices
yeah,
only. So when
yeah,
we
yeah,
enter the, I think that part, so directly maybe it is also a mapping, something like that only,
yeah. Yes, you're
matrix
right.
form.
Yeah,
Okay. So we'll continue next time then, I
yeah,
think.
yeah. We will continue.
Okay. Thank you, sir. Thank you. Good
Okay,
night, sir.
good.